today, and so I swear it was so much fun. And like I'll try to basically give that the moment of fun to you guys too, right? I'll try to explain it in the the best possible intuitive way. Yeah, right. Where there's nothing sort of like random maths magic, something like that. I'll try to make it like as simple as possible so that everyone might be able to enjoy this. Okay, so let's begin. So first of all, we want to find this sum, which is also called the Basel problem, right? And this is basically the sum of inverse squares, right? So 1 by 1 square plus 1 by 2 square plus 1 by 3 square up to infinity. This sum actually converges, right? Which can be found from the p-test. Again, you might know what p-test is, right? Now you can basically google it or just assume it converges for some time, and the answer is pi square by 6. Yeah, and we want to prove this result was first proved by Euler, right? They first showed that this sum is actually equals to pi square by 6. You can also check that by taking a partial sum, let's say from n equals to 1 to 10 or 20, and you will see that the answer is almost equal to pi square by 6. So that's how you can convince yourself. Now, first of all, I will prove that this sum is equal to the integral, and then we will evaluate this integral and get this value. So that's how we are gonna do it. There are other ways too, like there are ways to prove it using complex analysis, like that's on black pen red pen channel, right? Then there's also Euler's own way, which is using sign product formula, and now we are using double integral. Yeah, there are a lot of ways. And this one is actually pretty cool and easy. So let's start. First of all, we'll prove that this integral in the sum are equal. So we have integral from 0 to 1, integral from 0 to 1 of 1 by 1 minus xy dx dy, right? Now we know that x just goes from 0 to 1. So the modulus of x is less than 1. Also, the modulus of y is less than 1. Right? And if modulus of both of these things are less than 1, obviously their product will also have modulus less than 1, right? So since it has modulus less than 1, we can write it as infinite geometric series. Sum from n equals to 0 to infinity xy to the power n. Notice that over here the first term is xy to the power 0, which is 1, which is what should have been here, because the formula is a by 1 minus r, right? For infinite geometric series with first term a in the ratio r, right? And over here, yeah, obviously the first term should be 1, which is what it's there in the sum, and the ratio is xy, which is what it should have been. Okay, now I can write it as dx dy. Okay, interested in the sum and the integrals, right? And then integral from 0 to 1, 0 to 1, x to the power n, y to the power n, and then dx dy. Now, if the integrand is product of the functions of x and y, if the product is clearly like not composite or like merged with each other, we can integrate them single, right? We can do that. Yeah, so we'll just integrate it one by one, and we know that this is just x to the power n plus 1 by n plus 1 from 0 to 1, y to the power n plus 1 by n plus 1 from 0 to 1, right? And sum from n equals to 0 to infinity. Now if you are wondering why we can do this one is actually pretty simple. Like if let's say this question a to b, c to d, and this here is f of x, g of y, and then let's say if there is dx dy. Okay, so first of all, the first inside integral is in terms of x, so I can take gy out, right? So we'll have integral from a to b, g of y, and then we have this inside integral from c to d, f of x dx, and then dy, right? Now again, this will be a constant, right? So this can again be taken out of the integral. So we'll have integral from c to d, f of x dx times integral from a to b, g of y dy. So this is why we can do it. This is pretty simple reason. Okay, now let's evaluate this. We have 1 by n plus 1 minus 0, right? And again we have 1 by n plus 1 minus 0. So that gives us sum from n equals to 0 to infinity, n equals to 0 to infinity of 1 by n plus 1 square, which is sum from n equals to 1 to infinity of 1 by n square. So yeah, the equivalency of the sum and integral is proved. Now let's try to go ahead. Oof. Okay. So okay, now we have integral from 0 to 1, 1 by 1 minus xy dx dy. Now the integrand is okay. Now if you try to integrate it, you will get it in terms of log, right? Okay, so you will get it in terms of log, since it's in terms of x, 1 minus xy divided by minus y, and then you will get this is from 0 to 1 times dy, right? Now integral from 0 to 1. Now how will you do this? Okay, so this is basically log of 1 minus y by minus y minus plus log of 1 by y dy. We know that log of 1 is 0, so this is 1 ln of 1 minus y by minus y dy. Now those of you who know that basically this is my 0 to 1 minus ln of 1 minus y by y dy, this is actually a popular integral, yeah, which is if it was z over here, and then if it was like this should just have been li2 of z function, right? So this would just be li2 of 1, and we know that li2 of 1 basically if there is lis of wait, if there's basically this is like there's just wait, like just bear with me, like I do have an alternative way too, but this way also works. If you don't know about this li function, which is also called a polylogarithmic function, I have alternative ways too, like just bear with this function even if you don't know. This is called polylogarithmic function. Okay, now our polylogarithmic function base s of 1 is equal to zeta of s, so that's why this will be zeta of 2. Okay, so we just came back from where we started. Now we don't know value of zeta of 2. This is basically defined as zeta of 2, right? This is just the definition of zeta of 2. So we saw that if we try to evaluate it directly, we again get back to the same. We now need to find the same sum, right? Now what we got is we first of all we saw that this sum is equals to this integral. Now again, when we try to evaluate this integral, we got this sum, so it's kind of feedback loop, right? So that just means that we were not really able to find the answer, because like one's just leading to another. So what we will try to do is we will try to change the integrand. We will try to change the form of the integrand which it is in right now. So we'll try to do that. But how do we do that? Okay, let's see. Hey guys, and if you don't know about the polylogarithmic function, you can get that answer even by just applying the series of log. We know that minus ln of 1 minus x, the series for this is y plus y square by 2 plus y cube by 3, and so on, right? So when using this series, divided this series by y and the integrand, and then find the integral. So let me show you y plus y square by 2 plus y cube by 3 by y dy. 0 to 1, 1 plus y by 2 plus y square by 3 plus y cube by 4 dy. Now if I integrate this, y plus y square by 2 square plus y cube by 3 square plus y to the power 4 by 4 square dy, right? Now if we evaluate the integral, this is 1 by 2 square, 1 by 3 square, 1 by 4. So you get the same sum, right? So yeah, you don't really need to know about the Poill logarithm function. You can even just solve by the series itself, right? So anyways, the summary was, yeah, the integral leads us back to the same sum. And like, how do you find it? Now we'll try to change the integrand. Like there's like, I'll show you how. First of all, notice that like this integral basically, x goes in this integral, x goes from 0 to 1. Now y also goes from 0 to 1, right? Now in this domain, we have to integrate the integrand like 1 by 1 minus x. So basically, if you try to see it as volume, this is basically gives us the domain, where domain, and in that domain we have like a 3D object with height as 1 by 1 minus xy, and with that height we are trying to compare the volume of that 3D object, right? So now how we can transform this integral is like, okay, so the reason we are transforming is the first of all, know the reason why we are transforming, because in the hope that we will get some different kind of integrand which will be easier to compute, so that we can find the value. So that's our goal. And now let us see how we can do that. What I will try to do now is, I will try to rotate our domain of integration, right? Now basically, let's see, this is our like xy, the coordinates in our like the present system. Let's say this is x coordinate system, this is a ub coordinate system. Now if I want to rotate this one, if I apply, let's say if I want to rotate by 45 degrees, cos 45 sine 45, and then I will also show you like how this works. Like just bear with me for some time. Cos 90 plus 45 sine 90 plus 45. If I multiply this with ub, okay, now let me show you. Let's say over here in ub coordinate system, I have a 1 by 1 square again. If I have a 1 by 1 square, right, which okay, this is 1 1 1 1 square root 2, and this is 45 degrees, right? And this is 45 degrees, okay, and this is 90. Okay, if I have a like 1 by 1 square in the ub coordinate system, now after I apply this transformation to the coordinates ub, that will basically go to xy, right? And like you should have know, like, I mean, it's better to know that this first thing is where your like this u coordinate or like I coordinate or whatever you say, this u coordinate will go. So that means u coordinate will rotate by 45 degrees, and already the b has an angle of 90 already. So if I like, okay, so what I'm trying to say is, this is where our I and j will go. I mean, this is where our I will go, not j. Our I is this component over here, j is this component over here, right? So this is where our I will go. Cos 45 times cos 45 sin 45 is over here, right? So over here, if this I is going over here, obviously this line will go over here in this coordinate system, right? And also this will go over here as it goes over here. Okay, so yeah, this is where our I go and this is where our j goes. And since j has angle 90 plus 45, 90 plus 45, so this y coordinate system will also rotate by will also be in 135 degrees, which is over here. So it has rotated by 45 degrees, right? So that's that which is why this is called like rotation matrix by 45 degrees. I don't know how much I was able to make you clear on this. If you were already clear, then you might have got some insights. Otherwise, it might not have been helpful. I'm sorry for that. Okay, yeah, basically in our class they already knew that this was rotation matrix, so it wasn't hard for me, like, because I just told them that yeah it works, and yeah they said also yeah okay yeah it works. Okay, anyways, this is where I go, this is where J goes, and since J has angle of 135, so I'm making that 135 over here, right? In the rotated form it has angle 135 and it will have angle 45. Okay, so so our UV is over here, so if I rotate this entire square at 45 degrees in positive direction, we will get this one, right? So that is what this matrix multiplication or matrix vector multiplication or transformation says. If I multiply any coordinate in UV by this matrix, I will get xy, and that's what it exactly says over here, right? Okay, so I'm going to apply this transformation, uh, and the good thing about this transformation is it's just a rotation transformation, right? So in rotation transformations, the areas will be preserved, like the areas will not be multiplied or like reduced. Nothing will happen. Just over here, let the du db in this case will just be same as the dx dy in this case. dx dy is equals to du db. Since it's just rotation, like the in the rotation transformation, since the areas will not increase or decrease or nothing such will happen, so the dx dy in that area will just be same as the du db. The one step in the u and v direction, like just a du step in u and v direction, du db, this area will be same. So yeah, basically that's a feature of rotation transformation. I know I'm having a pretty bad explanation, but yeah, it's fun. Okay, now xy cos 45 is 1 by root 2, sin 45 is 1 by root 2, cos 135 is minus 1 by root 2, sin 135 is 1 by root 2, right? UB. Okay, now xy, what I'm basically trying to do is I'm basically trying to go from x to I'm trying to write x and y in terms of u and b, right? So yeah, now this will be u minus b by root 2, u plus b by root 2. So yeah, this if I make this substitution, that will rotate x and y coordinates by 45 degrees in clockwise direction, right? U and b in anti-clockwise, but x and y in clockwise direction. Okay, now okay, so now we have done this. Now we know that the substitution x is x is u minus b by 2, y is u plus b by 2, and in this change our dx dy will just be equals to du db, right? So we know this thing, and also we need to know about limits. Now in this new system, our domain is this one, right? And out this height of the function, the height for the 3D object, the one we can know what that will be. That will just be 1 minus, this is u minus b by root 2, u plus b by root 2, which is 1 by 1 minus u square minus b square by 2, which is 2 by 2 minus u square plus b square. So this is our height, right, guys? And yeah, I remember something more. Like if you actually want to verify this algebraically, if the intuition like it doesn't help you, if you want to verify this algebraically, you can also use the thing called, wait, what it is called? You can also use there's something called, there's a determinant. I forgot the name though. Oh wait, I'm sorry. Actually, the what it is called? Okay, okay. Anyway, I know the determinant, though I don't know its name. So now, okay, how we can do that is like dx dy, we can find this as partial derivative of xy divided by partial derivative of uv times du dv. There's a modulus, and this thing over here, this is defined by a determinant, which is partial x partial u, partial x partial b, partial y partial u, partial y partial b, du dv. And we know that partial x or partial u is just in this case, since x is u minus by root 2, y is u plus by root 2, partial x or partial u is just 1 by root 2, partial x or partial b is minus 1 by root 2. Yeah, this is called Jacobian matrix determinant. I just remembered, this is called Jacobian. And yeah, I think, and like this area, the way this determinant works will be much clear if you look at it as like transformation, right? If you know, if you have like, if you know how to look at transformation in linear algebra, like it will be much clear. It's just it's just the way that I told that the ratio of the areas which is given by determinants. Yeah, you can definitely look into that if you want more concerts, but it was not required for a problem. So yeah, we will not go through it right now. So this is just 1 du db. So you see that dx dy is just du db even from the calculations, right? Okay, now yeah, so we found out what the function will be, we found out what this differentials will be. Now the domain. About domain, notice that since this has 45-degree angle, this line will just be y equals to x, this line will just be y equals to minus x, right? And this, since this point is root 2, this line will be y is equals to, and the angle is 135, the slope is definitely minus x and plus root 2, right? This one is, slope is, oh sorry, this has positive slope because we need to see this angle, right? 45-degree. Okay, so this is x plus root 2, right? Wait, no, x minus root 2, because it root 2, y has to be 0, right? And this one, it has negative slope, so at root 2 y has to be 0, so plus root 2. Okay, yeah. So now how I can write the like domain for domain of integration is, let's divide this into 2. In the middle we have 1 by root 2, right? So while u goes from 0 to 1 by root 2, b goes from okay, I don't know why I wrote x over here. This should have been u actually. These things now, it's a man, this is b is equals to minus u, b is equals to u, and similarly over here as well, because this is, we are now in uv world. Okay, while u goes from 0 to 1 by root 2, b goes from minus u to plus u, right? And then this is db du plus, here's our integrand. We know that this is just 2 by 2 minus u square plus b square, and this is 1 by root 2 to root 2. B goes from x minus root 2 to root 2 minus x, 2 by 2 minus u square plus b square. Definitely this looks complex, but yeah, this will be easier to evaluate and this will give us our required answer, right? So definitely after all this hard work, now we are finally going to solve the Bessel problem that was unsolved for a lot of decades, you know. So yeah, we need to do some hard work for some good results, right? Yeah, okay. So let's solve it. It will not be that hard. I'm pretty sure this is the easiest step in the entire problem. Yeah. Okay, let's do the first one first. So the first one, but this is in terms of dB, right? So since this is just a, so b square plus a square So 1 by a tan inverse. Also notice that since u is less than root 2, so yeah, we can write it like this, because yeah, obviously u is less than root 2 over here in this domain. So yeah, so tan inverse b by square root of 2 minus u square, going from minus u to u du, right? So 2 times integral from 0 to 1 by root 2, 1 by root under 2 minus u square. So you know that we should evaluate u and minus evaluate minus u, right? Now, okay, let me do it. Let me not just like speak everything and not do anything. Minus tan inverse minus u by square root of 2 minus u square. Now, since tan inverse is odd, the negative sign comes out and that will become positive. So I will have 2 tan inverse u by square root of 2 minus u square du. Now, to solve this, just make a simple substitution. You can substitute u as 2 sine theta, sorry, root 2 sine theta, right? If you make that substitution, basically all the things are gonna simplify out now. If you make that substitution, what will you get is 2. Now over here this will be 0 to pi by 6, right? And this will be 1 by root 2 cos theta times 2 times tan inverse. This is root 2 sine theta by root 2 cos theta, and du is root 2 cos theta d theta. Root to cancel out, cos to cancel out. See, because the thing is, because it has to give us answers, so it has to simplify. It's just like we are like pressurizing maths. We are just like making pressurizing maths to give us the answer because it has to. There's no other way for it. Okay, now let's do it. 4 times this is theta square by 2, going from 0 to pi by 6. So this is 2 times pi square by 36, which is pi square by 18. Okay, so we got that the half of the not the half area, because the height is different for different cases. Even though the domain area is half, the volume is not half, because the height is different in this different like section. Okay, so now let's do other integral. It's similar. So plus over here, this is going from 1 by root 2 to root 2. I hope you got this right. Like, do you want to have a look at it? Okay, so let's do it. And the integral is from u minus root 2 to root 2 minus u. 2 comes out, and then 1 by 2 minus v square. It's similar, like go with the same approach. 1 by root 2 to root 2. 1 by root under 2 minus u square. Tan inverse b by root under 2 minus u square from u minus root 2 to root 2 minus u du. Okay, just continue with the same approach, and if you use the fact that this tan is odd, you will just get that because this is just opposite of this function, so it will just be 2 times tan inverse root 2 minus u by root under 2 minus u square. You will get this thing. You can check it yourself. Okay, now again we will make the substitution, right? And this time I will make u as root 2 times cos theta. Is that right? Yeah, I'll make this substitution. There's a reason, you will just see in some time. So 2, now this will be pi by 3, and that will be 0. And this is root 2 sine theta, then 2 tan inverse. Now root 2 1 minus cos theta by root 2 sine theta, right? And then du will be minus root 2 sine theta d theta. This minus sign can be used to reflect the integral from 0 to pi by 3. Now root 2 cancel out, sine to cancel out. There's a 2 tan inverse. Root 2 cancel out. 1 minus cos theta is 2 sin square theta by 2. This is 2 sin theta by 2 cos theta by 2, right? E theta. This is 4 times, again 2 cancel out, 0 to pi by 3. This is just tan inverse of tan theta by 2. Tan and tan inverse, they are same as being cancelled. Theta by 2 d theta. 4 times, this is theta square by 4 from 0 to pi by 3. Cancel. Pi square by 9 minus 0, so pi square by 9. And the reason I just, this time I use cos theta instead of sin theta is, so that 1 minus cos theta is gonna be sine, yeah, and I know that this is gonna give me sine because, yeah, and because if I had one, if I used sine, 1 minus sine, that would not have been breakable like it was with 1 minus cos. If I had 1 minus sine, I have to change that to again 1 minus cos pi by 2 minus x. So yeah, that would be hard. Now, so we got these two different parts, and now the only thing that I need to do is to add these two parts. Yeah. So if I add these two different parts, this is pi square by 18 plus pi square by 9, which is pi square plus 2 pi square by 18, which is 3 pi square by 18, which is pi square by 6, which is exactly what the answer is, the zeta of 2. And this solves the integral over here, pi square by 6, also this integral, also this sum, and a lot of other cool results. Yeah, so we have finally proved it. As usual, my explanation wasn't that good. These steps are a bit hard for me to explain right now, and I do hope that I will get like better at explaining over time. But I do feel like if you had like a little idea, a little background about this topic before watching, I do hope that you should have understood this one, right? So this is how we do it. First of all, we just try to change it to integral and then evaluate it in a different way, in a different domain, by rotating or anything like that. Usually rotating is done because the dx dy is preserved, like that will be same as du dv, so that's the reason we just rotated. And yeah, when the integrand is slightly different, like it's likely that it can be evaluated, and yeah, if you are like good enough to evaluate this, you get the answer. So that it is. So we have like completed the solution. Yeah, and hope you enjoyed the video. Thanks for watching. If you like it, like do so with your friends too, and look forward to seeing you in the upcoming videos.